All right, so finite element first principle review. So any guesses as to who this is? Pardon? Newton, yes. Sir Isaac Newton. So he developed what, first, second, and third law of physics, right? The body will remain at rest and will continue, right? As long as there's no unbalancing force acting on it. Which law is that? First one, right. Second law, acceleration of the body will be proportional to the result of all forces and in a direction or in the opposite direction of the resultant. Third law, action and reaction forces between interacting bodies will be equal in magnitude and collinear. So we have lots of forces or different forces acting on our different bodies, right? Everybody remembers the famous Hibbeler blobs and our equations of equilibrium. So we're mostly dealing with static situations, so we're going to have to be in equilibrium. The O represented here is our point of rotation or center of gravity, right? So moment of inertia for an area, and you should remember that from 311 or 312. That's the next one. Okay. So, examples of where we use area moments, dealing with beams, a submerged wall, or our bar in torsion is going to be a polar moment of inertia as opposed to a rectangular moment of inertia, right? And then parallel axis theorem. What are we saying when we have, or when we're talking about parallel axis? We're saying that if we know the moment of inertia of our main axis, then we can determine what the moment of inertia is at our parallel axis, right? Or moment about that parallel axis. And x and y are the rectangular equations, j is the polar equation. So this should be familiar stuff that you're used to seeing from many moons ago, yes? Okay, and we use those area moments to combine and determine the composite moment of inertia for a composite shape. So for rectangle B, we can just take the area moment. For rectangles A and D, we're going to have to apply what?
Parallel axis.
The parallel axis theorem, right? So you'll sum those all together and you can obtain the moments of about the x and the y axis. So stress and strain, P over A, that's tattooed on everybody's brain, right? What kind of, so this we're talking about normal. So normal is going to be perpendicular to the cross-sectional area, and we're making a few assumptions when we're dealing with normal stress. Anybody remember what those might be? Okay, we're going to say that the material maintains its orientation before and after the loading, right? The cross section maintains its plane, and we're not, I mean, the localized distortions, St. Benet's principle, right? We're going to move away from those and just as a reminder, you want to be, for St. Benet's principle, to get away from that localized stress concentration, you have to move the width, at least the width of the material away from the edge. And we're also, the other assumption is we're saying that P is along the axis of the material, and our material is homogeneous and isotropic, right? So homogeneous is the physical and mechanical properties throughout the volume are the same. So think of steel. Isotropic means that the homogeneous properties are in all directions and they're the same in all directions. So steel again. An example of anisotropic properties would be something that gets cold worked. So like cold drawn steel won't have the same properties in one direction versus the other. The other assumptions we make are that our, remember, it has a uniform cross-sectional area. We don't have any discontinuities or changes in cross-sectional area. And if the calculation is done in compression, the member must be short to avoid buckling. And when we talk about buckling, you have to go to buckling theory. So we'll get to that later. But those are the assumptions that we're making when we're dealing with just regular stress. Shear is going to be, normal stress was perpendicular to the cross-sectional area. Shear stress is parallel to the cross-sectional area. And we have to have our shear element be in equilibrium. So we have shear forces on all four sides. And examples of that shown there. So speaking of elements, our stress or strain elements, 2D and 3D. Remember that tension is considered positive, compression is negative, shear is considered positive if it's attempting to rotate the element. Well, it can rotate the element clockwise or counterclockwise depending on which convention you're using. You just have to be consistent about it. But it's indicated on the arrow on the right face of the stress element. So along with our element, we're dealing with principal stresses. So Moore's circle. The original stress element is based on the loads and geometry of what we're dealing with. The principal stress element, sigma 1, is the maximum. Sigma 2 is the middle, and sigma 3 is the minimum stress. So we're going to be dealing with 3 axes, not just 2-dimensional. And they, sigma 1 through sigma 3 are ordered from the most positive to the most negative. Biaxial or plane stress is what's shown in figure 4.6. And if 2 of the stresses are 0, then it's uniaxial stress. Triaxial stress or combined stress is shown in figure 2.7b. And remember, there's no shear in the principal stress. The maximum shear stress element provides the value of the greatest shear, and it's always 45 degrees from the principal stress angle because shear failure is at 45 degrees. Stress or our strain, we have linear strain and shear strain or normal strain. So if we have a linear strain, it's looking at something, the change in the elongation or contraction of a line. Shear strain is the change in angle between 2 line segments that were originally perpendicular to one another. So we apply that here with Hooke's law and our modulus of elasticity. And most of the time, we're trying to stay below the proportional limit so that our material doesn't go plastic and deform. So much of our analysis is trying to maintain the being in the linear portion of our curve. E is, of course, the modulus of elasticity. G is the modulus of rigidity for shear. And under uniaxial loading, if we combine the formula for stress and strain, we obtain, in Hooke's law, then we obtain the deflection formula, PL over AE. Right? So when we have uniaxial strain and we're within Hooke's law, then we have some lateral strain that we call, or is part of Poisson's ratio, and they're defined here. The three elastic constants, E, G, and nu for Poisson's, are related in those bottom two equations. And we have a table of strain values to principal stress and how to calculate them, just sort of reference material. Now, bending. So we're dealing with my over I or MC over I. And again, we're making some assumptions, right? That the material is isotropic, homogeneous, and that our material is going to obey Hooke's law. In this depiction, M is positive because the beam is making a smiley face. Following the right-hand rule, M acts in the positive Z direction. Positive Y or C values need the negative to follow the convention and have the beam above the neutral axis be negative to indicate compression, and then positive on the bottom to indicate tension. And the neutral axis is the horizontal cross-sectional line about which the area moments are equal. When we're dealing with curved beams, it changes a little bit. The neutral axis is no longer located along the centroidal axis of the cross-sectional area. Positive bending moments are attempting to make the radius larger or straighten out the curve. And the stress distribution is not linear as it is for a straight beam. And the maximum stresses are at the surfaces, top and bottom. Shear, when we have pure bending, there's going to be shear along the axis. Q is the definition of the first moment of the area of section that's being traversed. And T is the thickness or the width at that cross-sectional area. And maximum shear is at the neutral axis, and zero shear stress is at the edge of the cross-sectional area. And here's an example of the first moment with respect to the overall centroidal axis, and the area is the numerical representation of the integral of the area above the neutral axis. Now when we're dealing with shear, again we're assuming that this elastic behavior, we're maintaining a straight plane, parallel and radial, and then we can say that TR over J is going to apply, or TL over JG. J being the polar moment of inertia, G being the modulus of rigidity. And our max shear is going to be at the surface of our bar. Hoop stress and longitudinal stress. We're always going to measure hoop stress depicted in B, some distance away from the end cap so that we're not getting any of that discontinuity. The pressure P is always assumed to be uniform throughout. Our thickness of the wall T must be a ratio of R over T greater than or equal to 10, or T can be 1/20th of R, the radius. Most of the time we consider this in a biaxial state, but it can also be considered in a triaxial with a radial line, the radius or the radial being the thickness of the material, but that's usually pretty small compared to the hoop and the longitudinal stress, so it's usually ignored because you're looking at the pressure, or the maximum stress is going to be the pressure on the interior of the wall, and then it's going to be 0 on the outside of the wall. So there's not a lot happening there. So it usually gets ignored. When we're dealing with the sphere, the only difference is there's no hoop stress, it's all longitudinal. We can also use these principles when we're looking at interference fits, right? And look at the pressure as the radial interference, and it can also account for dissimilar materials. So those same principles will apply for this. And one last one is contact between two bodies. This is a pretty complex scenario and it's nonlinear, so this is why finite element analysis specifically would be used for this kind of scenario. And you can resolve it analytically or with analog calculations, but only a few very specific examples. The other stress states we have are thermal, right? If it's unconstrained, then our volumetric expansion or contraction, the stress state will be 0. If it is constrained, then our stress is defined by the equation listed on the slide, and with alpha being the material coefficient of thermal expansion. We also have stress concentrations, and they constitute any discontinuity in the material, surface, or cross-sectional area. And these discontinuities create localized stress. And stress concentration values are developed through empirical testing, and charts are then created for reference. So a lot of those you just look up on charts or on the internet. We're also concerned with material properties, so making sure that it's isotropic, and we need to know our modulus of elasticity. Strength is our inherent property of the material, and that governs our overall performance, so that's why it's important that we know and understand that. Well, I guess I'll just start at the beginning. So for material properties, we're concerned that they're homogeneous and isotropic, meaning that they have the same properties in all directions. Anisotropic is you have properties that differ in 2 or more directions, and orthotropic is when you have orthogonal planes and your properties are different in those 2 different planes. Composite materials would be a good example of that. Our modulus of elasticity and rigidity and Poisson's ratio are important to our analysis because that's what defines the material properties. We always want to make sure that we're, careful that we're able to distinguish between ductile and brittle materials. So when we're considering ductile materials, we're looking at the ultimate strength and tension and compression are about the same, and we have elongation values that are greater than 5%. If the material is brittle, then it tends to fall into the categories of the bullet statements under brittle. So when we're dealing with ductile failure theory, these are 3 examples, the max norm, max shear, and distortion energy failure. Most of the time for finite element analysis, we're dealing with the distortion energy theory. But I mean, the others can be used, but most of the time we're trying to deal with distortion energy, or von Mises is the other term that's used for that. When we're dealing with brittle failure theory, we're looking at the max normal, coulombs, or modified Moores, and they're defined by those graphs. And most of the properties are for compression, which is where brittle materials work better. We also have to deal with buckling theory, right? So if we have an increase of P over the critical stress, then we're going to have a collapse of the column, and we're always looking for the least radius of gyration as it relates to the cross-sectional area, and we have to check that the slenderness ratio is greater than the column constant for Euler's, and then we also have to check the critical stress. Critical stress is governed by the yield strength of the material. If we're dealing with a short column, then you're going to use Johnson's formula. And when we're doing FEA, the buckling problems will be non-conservative for columns that are not Euler's equations. However, as long as the operating stress on the non-Euler column remains below the yield point, then buckling failure is not possible. Eccentric loaded columns require that we use the eccentric loading column or equation. We also have a fatigue failure mode, so we're trying to get below the endurance strength of the material. We have some sort of fluctuating stress that we're trying to cope with, and the 3 things that we have to make sure that we have a handle on are number of cycles, the loading history, and whatever safety factor we think we want to use for fatigue loading. If the mean stress is anything other than 0, then we're going to use the Goodman equation for solving for our safety factor, and we can also apply Miner's rule, which is the damage accumulation. So when we're applying fatigue loading to ductile materials, The basic structural changes that occur, and in this order, are you're going to have a crack initiation, localized crack growth. The crack growth then goes into a high tensile area, and the crack proceeds across the section and begins to propagate. And then you have ultimate ductile failures when the crack just ruptures. So we also have to be aware of creep. So that's time dependent, and it's plastic deformation under a sustained load. The eta symbol in the equation is the material's coefficient of viscosity. The change in strain over time is the strain rate. The instantaneous elongation is normal deformation under applied load. Primary creep is the strain hardening. Secondary creep, which is the minimum creep rate and the longest time duration on the curve. And tertiary creep is the material begins to neck and create voids and then ultimately fails. When we talk about creep strength, we want a stress that produces a minimum creep rate of 10 to the minus 5% per hour. So a pretty small value. And dynamic analysis will be outside the scope of this course. Everything we're doing is going to be static. So basic engineering fundamentals should be referred to throughout the analysis process. Take the time to understand the nature of the engineering problem, what first principles will govern the analysis, how can they be qualified and quantified, where is the highest stress most likely to be, will a sample manual calculation solve the problem? You don't always have to do finite element analysis. Sometimes some simple hand calculations will solve the problem for you. We also have to consider what kind of stress state will be caused and the geometry and boundary conditions for the model. Can the geometry be simplified? What type of stress and what's its orientation? X, Y, and Z are principal stresses. We want to verify that the boundary conditions make sense. You're always going to draw a free body diagram. And you have to consider your confidence level in the loads. What's your safety factor going to be? Prior to obtaining your FEA results, you're going to attempt an analog calculation to provide you context and validation of your FEA data.